knowing a certain piece of information is often less useful than being able to figure something out. Here's an example. If you take a point on the edge of a wheel and trace out its path as the wheel rolls, you'll draw out a curve called a cycloid. A cycloid might look like a slice taken out of a circle, but it is a unique kind of curve. So how could we work with this curve and figure out something such as the area contained between the cycloid and the ground? A good way to understand something complicated is to break it apart into simpler pieces. So what do we know about this shape? First off, it was traced out from one rotation of a wheel. Every complete rotation of a wheel takes it forward a distance of one wheel circumference. That makes the width of the shape one circumference. We can measure a circumference in terms of the circle's radius. It takes just a little more than 6 radii to stretch along the circumference. More precisely, 2 pi radii. The height of the shape is the same as the height of the wheel, which would be 2 radii. For the time being, let's ignore the curving sides and trace out edges from the top center of the shape to the bottom corners, making a triangle. The triangle has a height of 2 radii and a base of 2 pi radii. We could chop this triangle in half and refit the area to make a rectangle measuring 2 radii by pi radii. The area is 2 times r times pi times r, which gives us 2 times pi times r, or 2 pi r squared. That gives us the centerpiece, but we're still left with 2 round lobes on the sides. The shape is symmetrical, meaning these 2 lobes are mirror copies of each other. We could fit them together to make a sort of pinched oval shape. We used the circular wheel as the basis for measuring the triangle. So let's see if we can do the same for this piece. The pinched oval shape has the same height as the circle. But what about the width? Both shapes do have a continually changing width, going from small to large to small again. If we play with this, we could find that spanning upwards, these shapes have identical widths. If we sliced up the pinched oval into tiny slivers, we could slide those slivers over each other to make a perfect circle. That means that this shape has the same area as this circle. We can find the circle's area by breaking it apart into smaller and smaller wedges. The wedges are 1 radius tall and stretch out to a width of 1 circle circumference, or 2 pi r. We can fit these wedges into a rectangle. The rectangle has a height of 1 radius and a width of 1/2 of a circumference, or pi r. The circle's area ends up being 1 radius times pi radii, for a total of pi r squared. The total area under the cycloid measures pi r squared plus 2 pi r squared, for a grand total of 3 pi r squared. So is this useful? Sure, all sorts of formulas like this do have unexpected practical uses. However, it is probably rare for someone to have a practical need for this formula in everyday life. But the real use for this, I would say, is as a mental exercise. The geometry is just a tool for exploring a problem-solving process. We're taking a complex thing and breaking it apart so we can see its patterns and understand it. Math can help give us raw thinking skills so we can face seemingly unknowable things, break them apart, and make them knowable.